These rectangular approximations we've been making are called Riemann sums. Okay. We'll get back to the actual area of this problem later on in this chapter. Okay. We now have an under approximation, over approximation, but in the process we use something called Riemann sums. I didn't mention it before, but this is their title. So I would like to develop a formula for them now, because that's a big part of what section 5.1 is about. So if we look back at what we constructed here, again, this was specific to 4 rectangles, right? Could be more or less. 4 rectangles, and the specific interval 0, 2, and the specific function, the squaring function, x squared. There's a few facets you have to know whenever you're dealing with any one of these problems. But you can still write a general formula for what's going on for any problem in this way. So if we look here, we had f of 0 was times delta x, f of 0.5 delta x, f of 1 delta x, f of 1.5 delta x. If we wrote the 0, the 0.5, the 1, 1.5 a little more abstractly, right? Those are specific values to this problem. But let's look back at what they really were. So this setup here, right? If we think about it, was something more like the function at where? Well, 0 was really the start of the whole interval, right? From 0 to 2 was our interval. So really, it's a, right? The letters we used were a and b for the endpoints and starting points of this interval irrespectively. So f of a, in a sense, right, 0 for our particular problem, times delta x, okay, plus the next one, f of 0.5. Well, I don't want to use a particular number 0.5, but I could say it's f of starting point plus 1 delta x in, right, times delta x. If we look back at the problem, in the picture, it makes perfect sense, right? Here I'm at f of a, and if I move 0.5 inwards along this interval, I've moved a delta x distance, so a plus delta x. I don't just want to call it delta x, because the fact that a is 0, right, a is 0 in this problem is specific to this problem. It could have been 1, right? It could have been anything. So we don't want to just write delta x down here for delta x, even though it's true for this problem. But in general, it'd be a starting point plus delta x gets you to the next location down, and you're evaluating the function at that new location. That's the height of the second rectangle, right? And then multiplying by delta x, right, gives you the base times the height of the second rectangle. Moving down a little bit further, the next one should be f of starting point plus 2 delta x's, right? That is, you moved another delta x away from this position, right? In the picture, here's a plus delta x. I'm moving another delta x, so that's a plus 2 delta x's in that I am. I evaluate the function there, so f of a plus 2 delta x times delta x for the base of the rectangle, right? Again, height times base gives me the overall area of the rectangle. And the last one is the same thing, just one more delta x in, so f of a plus 3 delta x for this particular problem, times delta x. The only thing specific to our problem at this point, right, is the fact that we have 0 delta x's is an important way to think about this structure here. This is like plus 0 delta x here, right? We have 1 delta x, 2 delta x, 3 delta x's. We only have 4 terms in our sum. That's specific to our problem at this point, and that's the only thing in this pile of symbols that's specific to our problem, is that we only have 4 terms, because we chose, or I chose, 4 rectangles. So if you chose any number of rectangles, right, it would be a little bit different. But we can write this now. Again, delta x can move to the outside of all this, right? So let's take delta x out for a moment. You've got delta x here, and then you've got this other expression, right? F of, again, I'm going to go ahead and fill it in here this time, a plus 0 delta x, f of a plus 1 delta x. I'm just going to write it outright, 1 delta x. Now let's just assume it's not specifically 4 rectangles, any number of rectangles, right? So what would happen here? Let's say it was in rectangles, right? Move from 4 rectangles to an arbitrary number of rectangles, in rectangles. Okay? Move to in rectangles, what would happen? Well, we'd have 0, 1, 2, 3, and you just keep going, right? Until how many? Well, you'd have f of a plus what? How many would you go through? Well, here, when it was 4 rectangles, we ended up with 3 as the last value here on delta x. So this should be n minus 1, right, if we're going to have n rectangles. That's because we're starting with a 0 value here, right? So we end up with n minus 1. From 0 to n minus 1 is in terms, right? Because we're starting at 0. It's a little confusing there, but should have n minus 1 in this last expression, okay? So now there's a concise way to talk about these types of summations, right? There's the summation symbol. So now we've got delta x times this sum of n terms, which should look like sum of f of a plus, the only thing changing in here is the 0, 1 until n minus 1. So I'm going to write that as an I, right? That changing object there. I delta x's. Right? Yeah. So this I goes from what values? It goes from 0, the first one, right? And we haven't moved from the left-hand side of the interval until we get to the very end when I will be n minus 1. So n minus 1 is the last step there. Okay? Now, even though delta x does not depend on I whatsoever, it's customary to write the delta x after this expression. Okay? So usually it's written like this. Sum I equals 0 to n minus 1 f of a plus I delta x times another delta x on the outside of the function. Right? Again, this is the base length to every one of these rectangles. This is a bunch of rectangles. How many? N of them, from 0 to n minus 1. These are n rectangles with their height times their base multiplied together to get their area. And this is what's called the left endpoint approximation. So I'm going to call it Ln. The book uses this notation, Ln. Right? It'll be n rectangles. I know it goes to n minus 1, but that's because you're starting at 0 in this formula. So this is now you consider to be a formula to be used. You won't need pictures anymore to help determine any of these features, right? The pictures are very cumbersome, very nice and helpful at first conceptually, but you don't have to rely on them to do these computations. Down here is our left endpoint formula for these types of computations. Okay?